All right, so the raw data from the oscilloscope is imported into MATLAB, and this is the a trace of the raw data. You can tell when the event begins. If we magnify in this area, you can see the change in frequency from DC to higher frequencies and even higher frequencies. That implies that the object is still accelerating. Lasers on. Where's the offset? There we go. Okay. Give me some wigglies. Beautiful. Alright. A little faster. So we see the frequency goes up with velocity. Alright. So using the MATLAB spectrogram command, we can take a Fourier transform of that raw data, looking at the frequency over a windowed sample, and plot that the highest power spectral density component in that window and assign a frequency to it. So now we've got a plot of in the frequency domain representing velocity. You can see this is the acceleration here to there over time on the x-axis to frequency on the y-axis. So this point here is a frequency of this 3 times 10 to the 8th, 300 megahertz.
Yeah.
Which corresponds to a velocity of, make it up as you go along. Otherwise known as 230 meters per second. Light originates from the laser, is ported into input of the circulator, which is then routed, all of it, to port 2, which is then sent towards the probe. The probe has a back reflector built into it that will send a little bit of the unshifted light back. The rest of the light goes out through the lensing, out of the probe. Some of it strikes the target, and that gets reflected as can be recollected. This now mixes with the unshifted reference light, enters back to circulator in port 2, and only goes around to port 3. So the light comes out port 3. This is now a heterodyne beat frequency between the two signals. And that varies the photocurrent in the optical detector. It gives us a varying electrical output, which is set to the oscilloscope, which can then record the varying signal from the photodetector. Typically, we'll sample this at 1 or 5 gigasamples per second.